So this is Engineering Statistics and Linear Algebra 18 EC44 Module 1 Lecture 5. We are studying the characteristic function under the single random variables. So when we talk about the characteristic function, it's just a, another special case which we generally represent it as phi x of j omega, where x is the random variable. So here the argument is the frequency in radians per second with a value j, right? So phi x j omega is equal to e to the power e of, that is the expectation of e to the power of j omega x. This is the expectation which we are talking about, and that is given by minus infinity into infinity fxx e to the power of j omega x dx. And the inverse of this can be considered as, right, we can just write the inverse of this as fxx is equal to 1 by 2 pi minus infinity infinity phi x j omega e to the power of minus j omega s j omega. So the characteristic function and the PDF they just form a Fourier transform pair. Okay, they form a Fourier transform pair. Now it's very important to consider that the 2.83 and 2.84 are different from the Fourier transform in the sense that only the omega gets reversed. That means if you see this over here, the Fourier transform pair looks something like this. F of omega is equal to minus infinity to plus infinity, f of t e to the power of minus j omega t. So you have minus here, and in the inverse you have plus. But here we have the exact other way around. Here we have plus and here we have minus. So therefore, there is in the argument we have the in the exponent portion we have the sign getting reversed between the characteristic function and the Fourier transform. Okay, Fourier transform. So this is just phi x j omega, and the PDF in terms of the characteristic function can be written something like this by considering the Fourier transform pair. So an important feature of the characteristic function is there are a few PDF for which the concept of mean and variance mathematically do not exist. So we see that for some of the distributions, we don't have mean and variance at all. For example, Cauchy's PDF. Then under that condition, the characteristic function of the random variable will always exist because a PDF is always non-negative and has a finite area of 1. Okay, characteristic function of a random variable will always exist because the PDF is always non-negative and has a finite area of 1. So what we have argument of this is, magnitude of this is always equal to 1. The phase of this is omega x, but magnitude of this is always 1, right? Similarly, the phase of this is, omega x, and the magnitude is 1. That is what it is. Thus, the characteristic function can be more general alternative description of a PDF than the mean, variance, and the higher order moments. So therefore, characteristic function becomes a very important term over here. That feature makes characteristic function attractive in the advanced probability topics. And there are a lot of other reasons we see that the characteristic function is useful other than this, okay, particularly with respect to the Fourier transforms. So using this property over here, let us try to solve some of the examples. So characteristic function for a random variable x uniformly distributed between 0 and 1 is using 2.63 over there. That means 2.63 will be the expression for the uniform value, right? So we know the uniform random distribution how it is. It will be between 1 and 0 and 1, the magnitude will be 1. If you take between y1 and y2, the magnitude will be 1 by y2 minus y1. That's the only difference between here 0 to 1 and y1 and y2. Here we are taking 0 to 1. So therefore, integral 0 to 1 magnitude is 1 for fxx, and we have e to the power of j omega. So if you try to integrate this, then you'll get e to the power of j omega x by j omega limits 0 to 1. And if you substitute 1, you'll get e to the power of j omega. If you substitute 0, e to the power of 0 will give me 1. So thus you'll get this function. If you want, we can simplify it much more by just taking out e to the power of minus j omega by 2. Then this will become e to the power of j omega by 2 minus e to the power of minus j omega by 2. And denominator will be just j omega. And that can be written as, multiply and divide the denominator by 2. Then this, e to the power of j omega by 2 minus e to the power of minus j omega by 2 divided by j omega by 2 will become something like, sin x by x kind of form. So you can, solve that and try to write it in terms of, what is known as the sinc function. Sinc function is sin x by x. So this can always be written in the form of a sinc function, or even for that matter, a sine function. Sinc function is sin x by x format. So you can convert this into sin x by x format. The characteristic function of a normalized Gaussian random variable can also be written in the same way. So for that, Gaussian random variable is exponential of minus z square by 2 tz. Then we have exponential of j omega x or j omega z for the z function. So therefore, this both are exponentials. So therefore, the exponentials are getting added up. So if we evaluate this integral, then we can find the value there. So to do that, you need to write the, you can just take out the value of e to the power of minus, omega squared by 2 over here. And then that means that you need to, this gets added inside. And hence, this gets added inside, and hence we'll get j minus j omega whole square by 2. Now this, change of variables, you can call it, where you can write z minus j omega as u is equal to z minus j omega, then you can write this expression. So you can see that this turns out to be equal to 1. This is just the value, total probability under the curve. Okay, total probability under the curve, and that term's value equals to 1, and hence we are left with e to the power of minus omega squared by 2. So thus, for a Gaussian random variable, we can, if you try to solve this in a proper way, that means by taking out this, you will have to compensate that for inside as minus omega squared by 2, right? And that will make the whole thing square over here, and change of variable by writing u equal to z minus j omega will give us this, and this is equal to 1, and hence we are just left with this. This is equal to 1 because the area under the curve is equal to 1. Total probability is equal to 1. Okay, area under the PDF curve is equal to 1. Total probability is equal to 1. Hence, we will get only this term over here. So, if we consider a random variable which is discrete with a PDF, then the characteristic function using this PDF will be, so discrete will be this expression over here for the probability, and e to the power of j omega x is what we have. So discrete function, and e to the for discrete function for the PMF or PDF, whatever you call it, and e to the power of j omega x, and then you can change the order of integration over here. And if you try to do that, then you will get the integration of this turns out to be just e to the power of, you just need to replace. When x is equal to xi, this value equal to 1. So therefore, we'll get e to the power of j omega xi. Okay, e to the power j omega xi. Pi remaining as it is. So this integral, if you evaluate, you just need to substitute within this x equal to xi, because we have x minus xi equal to 0. This we have in the del x minus xi. So hence we should write x minus xi equal to 0. That will make x equal to xi, and that you should substitute only within this, and this is equal to 1 at that time when x is equal to xi. So we'll get the expression for the what you call characteristic function as that. Then we can have a Bernoulli's counting random variable where we can write the Bernoulli's equation as the what you call probability density function is q del x plus p del x minus 1. Okay, e to the power of j omega x is the characteristic equations, this thing, and then dx. Then if you try to integrate this, integrating del x will give us just a value 1, q into 1. Integrating this value will give us a delay, which is e to the power of j omega. Okay, p e to the power of j omega. Suppose we take a transformation which corresponds to y is equal to ax plus b, then we can write the what you call characteristic function as e to the power of j omega y, and j omega y will be y. In place of y, you need to write ax plus b, and hence you can just try to expand this. This is e to the power of j omega ax, or e to the power of j omega x whole to the power a multiplied by e to the power of j omega b, e to the power of j omega b. So e to the power of j omega b is just a constant. You can take out that value, it will come out over here. Here you will get e to the power of j omega ax. Okay, e to the power of j omega ax. So now the value which is different over here is, in place of omega we have here omega a. We have here omega a. So therefore it is e to the power of j omega b into phi x j omega a. In place of omega we have omega a. So if x is, next example is, if x is a random variable uniformly distributed between 0 and 1, again we are taking equal to 1, then the transformation 2.67 gives the arbitrary uniform random variable with PDF shown in the figure. So using that, the characteristic function of the arbitrary random variable will be, you can try to write that, right? Here he is taking 0 and 1. Is a random variable between 0 and 1, then the transformation 2.67. If you see that, use the arbitrary, random variable with a PDF shown in the figure 2.3a. Let us try to see what is that 2.67. Okay, so 2.67 is this: y is equal to y2 minus y1 x plus y1. So if you take this equation over here and use it there, y2 minus y1 x plus y1. Okay. So here we have y2 minus y1 omega. That is why we have here. Now you just need to write, this one. So that will be e to the power e of, e to the power of j omega y. In place of y, you need to write y2 minus y1 into x plus y1. So if you simplify that, then you will get this term over here, right? So I'll just do the annotation and then try to write that over here. I think might be that will make things more clear. So this will be just e to the power e, what you call, of j omega y, that is equal to e of e to the power of j omega. In place of y, we need to write y2 minus y1 into x plus y1. So if you simplify this, you will get as e j omega y2 minus y1 into x multiplied by e to the power of j omega y1. And this is just a constant, right? So you can take it out, and that is what he has done here. And then this value, if you see over here, okay, in place of omega, you have omega y2 minus y1. That's why he has put y2 minus y1 omega. Omega into y2 minus y1 or y2 minus y1 into omega, right? So we'll get this stuff. Then you can try to, what you call, solve this, or you can find the integration for this, and the magnitude of that will be definitely 1 corresponding to that, and you can try to solve that and get the value. So this is, the value, whatever we have here. This value will be nothing but e to the power of j omega y1 integral. You need to write whatever is there in that, the what you call j of y2 minus y1 omega, right, and the fz value. Okay, you can try to solve that, then you will get this equation. You try to solve. If you don't get it, then we'll try to do that. Fine. So then I'll go for the next one. Just clear the drawing also. Okay. So then moments about the origin may be obtained from the characteristic function. To see this, we need to differentiate the 2.83 n times with respect to j omega. So if you differentiate this dn by dj omega to the power n, this function over here, then you are differentiating the function inside. So you'll get integral minus infinity to infinity x to the power n fx x e to the power of j omega x dx. Okay, if you differentiate that, you'll get x to the power n over here. Okay, in addition to whatever was there earlier to us. So this is nothing but, you can say that, e to the power of e of xn will be this whole thing when omega is equal to 0. Because when I make this 1, when will this become 1? When omega is equal to 0. Then whatever we are left with is just expectation of x to the power n. Okay? Okay. So moments about the origin may be obtained from the characteristic function. To see this, we need to just differentiate this, and then if you try to write omega equal to 0, in that we are going to get that. So whatever moment you want, if you want the nth moment, you will just need to differentiate the characteristic function n times, and then substitute omega equal to 0. Okay. Next, if the power series expansion is used for the exponential j omega, the characteristic function of the normalized uniform random variable can be expressed as, you can try to write the expansion for this as 1 plus j omega by 2 factorial plus 1 plus j omega squared by 3 factorial plus etc. etc. So this we have got it for the value which we might have written over here. We might have written over here for the uniform random variable. So you will get the expression like this: 1 plus j omega by 2 factorial plus 1 plus j omega squared by 3 factorial. This is e to the power of j omega. Okay, so you can try to write that, and then if you try to write expectation of x, which is only one times difference of this, one time differentiation of this, then you will get, this value will turn out to be 1 by 2 factorial. This value will turn out to be 0. This will be twice of j omega by 3 factorial plus, whatever. Then when you substitute omega equal to 0, all these terms will become 0. Only 1 by root 2 will remain. Similarly, if you differentiate it, two times, if you differentiate it 2 times, you are going to get only whatever is the term over here, only this, not factorial, whatever is this, because this term will be, if you differentiate it once, it will become twice of j omega. If you differentiate it once more, it will be twice of j square, okay, and that divided by 3 factorial will give us 2 will cancel, 3 into 2 into 1, therefore we are left with 1 by 3. Okay, so we'll just get whatever factorial. If this is the n factorial, then the second differential will be correspondingly will have that quantity. So thus the result in 2.92 and 2.93 are the same as those in 2.65 and 64 and 65, which we have calculated earlier, which are obtained directly by the integration. So you can check these equations, and these equations both are same. Then we come to the next example. The characteristic function for a Bernoulli random variable is given by this function. If you differentiate that, right, you'll get the differential of q as 0, and we'll get the differential of this as the same thing, that is e to the power of j omega, right? So that just means that the expectation of e of x, because this is giving us the e of x, single differential will give e of x, and that will be e to the power of j omega, whatever we have, but omega equal to 0, so that will give us the expectation or mean value equal to p. Similarly, if you try to differentiate this twice, again I'll get the same term there. So e of x square will be again this at omega equal to 0, that is equal to p. So we'll get the same result here, 2.94 and 95, as we have got in 2.80 and 2.82 for the Bernoulli's random variable, where any moment will just give you the value p1, e to the power e of x to the power n also will be equal to p in case of a Bernoulli random variable, which we have already seen. Okay. Let us try